returning to our complex numbers and this idea of the Moivre's theorem, which is something we've actually seen without calling it the Moivre's theorem. There it is. Cos theta plus I sine theta to the power of n is cos n theta plus I sine n theta. I say we've seen it before because all it's really saying is when you raise a number to the power of n, the argument gets multiplied by n. That's all it's really saying. And we've seen that. It just formalises it into a theorem. Now, de Moivre's theorem technically is just when the modulus is 1. Which makes it very limited, but it's very easy to then extend it out because all we're doing is putting the modulus in there, and obviously if we raise r to the power of n, we get r to the power of n. How does it help me? Well, something like this it could help me. 1 minus I to the power of 5. Sure, I could expand that out using the binomial theorem, and then I'd have to collect terms and things like that. But if I work out its modulus, and this is a nice one to work out, it's just the square root of 2, its argument would be minus pi on 4. And then if I use de Moivre's theorem, well, root 2 to the power of 5, and then I'd multiply the argument by 5, I get minus 5 pi on 4. Tidying up root 2 to the power of 5, I get 4 root 2 cis 3 pi on 4. And that's if I left it in mod arg form. But then I can calculate 1 minus I to the power of 5 very quickly by using cos 3 pi on 4 and I sine 3 pi on 4, and there's our answer. Okay, power of 5 is a small power, but imagine if that power was 10 or 20 or some really large number, expanding all that out. It's going to take a little bit of time, then even the substitution, collecting like terms, whereas this would be a lot quicker. So I guess the higher the power, the more valuable it becomes for things like this. Going back the other way though, instead of finding powers, we can actually use de Moivre's theorem to find roots of numbers. Because even though de Moivre's theorem was for the power of n, where n technically is an integer, I mean it still works when that power is fractional, so finding roots. So z to the power of n is x plus iy. I could change the x plus iy into the cis theta, so cos plus I sine. So to find z, it would be the nth root of r, but I would divide the argument by n. But not just the argument by itself, because you have multiple solutions. For instance, when we find the square root of a number, we know we get both plus or minus, we get 2 solutions. You will always get the same number of solutions as whatever the power is. Now, they might not all be real, some of them could be complex, and we simply just substitute in integers, consecutive integers, until we've got the required amount that we want. I mean, traditionally we start at 0. There's no actual reason why you have to start at 0. You could start at any number you like and then just have the appropriate number of consecutive integers that you substitute in. In fact, if you know the solutions are going to be in conjugate pairs, so you're finding the root of a real number, then it's probably more useful to substitute in plus or minus 1, plus or minus 2, because that'll bring out the conjugates straight away. Z squared equals 4i, well z squared would be 4 cis pi on 2, which will be pi on 2 plus 2 pi k over 2. I'd need 2 solutions, so I'll substitute in 0 and 1. And I get 2 cis pi on 4, 2 cis 5 pi on 4, which I can then work out, and there's my 2 square roots. That gives us another way of finding the square root of complex numbers. Of course, it does depend on the argument being quite nice if I want to get it into the x plus iy form, because can we find the cos of the angle a nice neat exact value or not? So when it's pi on 2 and pi on 4 and those sort of things, it works out nicely. Another way of thinking about it, our first solution would be 2 cis pi on 4, but one thing we know is that they're going to be evenly spaced around the Argand diagram. So the other solution, well there's 360 degrees all up, will be 180 degrees away. So there's my other solution. I could do it that way by plotting the first one and then just working out how far around the next one is. Z to the power of 4 minus 16 equals 0. This one is a real number, so I'll use the conjugate idea. I'll go 0 plus or minus 1 and then 2. That's what I'll substitute in. And I get my 4 solutions, and these ones are quite nice because 0 pi on 2. We're going to end up with 2i, minus 2i, and minus 2. So when we were just dealing with the real numbers, we would have said, oh well, it's just plus or minus 2. But there are two other solutions. They just happen to be, in this case, purely imaginary numbers of 2i and minus 2i. If I was to think about it pictorially, ooh, there's a fancy word. There's my first solution, 2. Now I know they're every 90 degrees, or pi on 2. So the next one I'll put there. I know they're in conjugate pairs, so I'll throw the next one down there, and then the fourth one must be over there. There's my 4 solutions. I have to find the 4 roots of 1 plus root 3i. Put it into mod arg, I get 2 cis pi on 3. They'll be divided by 4. In this case, I didn't worry about the plus or minus because 1 plus 3i, not a real number. So they're not going to be in conjugate pairs, this one, so it doesn't really matter. I could still do plus or minus 1. I mean, it doesn't matter. There are my 4 solutions. So 4 root 2 cis pi on 12, cis 7 pi on 12, 13 pi on 12, 19 pi on 12. Now, if you're leaving your answer in mod arg form, we usually then quote it in principal argument. So the 13 pi on 12 I would then change to minus 11 pi on 12, and the 19 pi on 12 I would change to minus 5 pi on 12. If I had to actually calculate it out, although this one's a bit tricky because what is the cos of pi on 12? I guess we could work it out using, alpha plus beta formulas, but too much work. But if it was a nice neat one we could work out, then I probably wouldn't bother changing it to principal argument, because the sine of 13 pi on 12 is going to give me the same answer as the sine of minus 11 pi on 12. If I'm not going to leave it in that form, why worry about changing it? I might as well just go straight to the sine of the angle that I've just found. On our argand diagram, there's my first one. Again, I know their 4th roots are every 90 degrees or every pi on 2. So there would be my next one. The third one would be over there. 4th one would be there. So as I say, they actually would lie on a circle. It's like we're going around a circle, the radius, whatever the modulus happens to be for the complex number. So that is de Moivre's theorem.